So when do you use non-parametric tests in general? Well, you use them when you don't have interval or ratio data, so you've got nominal or ordinal data, or your data violate the assumptions for the parametric test that you wanted to use for your study, so you collected interval or ratio data, but you ran into trouble. That's when you use non-parametric tests. So they were in the matrix of basic statistical tests. They were the ones that were not in the bottom row because those were your parametrics, so non-parametrics are above them. And they are the backup tests that you can use. They're right above each non-parametric test in case you get into trouble and you can't use that one. It's important you know that there is a backup solution. So we're really only going to cover two in depth, but you should know that they all exist just in case you need a backup. It happens to people all the time. So let's talk about the first one. The first one is called the chi-square goodness of fit test, and that symbol up top is chi-square, by the way, the X looking thing. So use the chi-square goodness of fit test when you have frequency counts for only one nominal or categorical variable. Can also be an ordinal variable as long as it's the IV. And then you have two or more levels, and you want to know whether the frequency in each level differs from some expected distribution. Usually what you want to know is this are the counts equally distributed across the categories of this nominal or categorical variable. So it is one of the weed whacker tests, as I refer to them. The backup, they're a little weird, but you know what? They've saved a lot of people's butts on their dissertation just knowing that they exist. So some examples are some sizes of Starbucks. You know, they've got tall, grande, and venti, purchased more often than others. That would be a chi-square looking across the four categories. I didn't even know I had Trenta. Are patients at a treatment center more often referred by a particular source? So county or courts or private therapists, you want to know, do we get equal distributions of clients from all those sources? That would be a chi-square goodness of fit. And then out of three possible answer choices on a test, A, B, and C, for example, is each equally likely to be the correct answer. So if you wanted to know if that was the case, you would do a chi-square goodness of fit test, and it will compare the counts across the categories and let you know if they're equal or not. So there are some assumptions of the chi-square goodness of fit test, and they're weird. And that's, again, why it's called like a weed whacker test. So the first one is not that weird. You've got independence of cases in each level or group, meaning each person or thing is only counted one time. You have a between subjects design. Now, here's where they get weird. The expected frequency for each category or cell or level is at least one. So you can't have categories where you don't expect at least one count in there. And then no more than 20% of the categories can have an expected frequency less than 5. So every category has to have at least one, and you can't have more than 20% of categories with expected frequencies less than 5. Whoa, those are weird. Hence, weed whacker test. So the hypotheses are written about frequencies of things because you're comparing frequencies across categories. So your null hypothesis is that the frequency in level 1 is equal to the frequency in level 2, etc., and so forth moving forward. All the frequencies are equal. There is no significant difference between the observed frequencies and what would be expected if the categories were all equally likely to occur. So there's some variation, but basically they're all equal. Your alternative is the opposite. They're not all equal. So this is an omnibus test, as you might guess. There is a significant difference between the observed frequencies and what would be expected if the categories were all equally likely to occur. This is an omnibus test. As I just said, it tests multiple things at once. If any category is different from expectation, it will be statistically significant. Now, if you reject the null hypothesis for the chi-square goodness of fit test, because it's omnibus, all you know is that at least one category has a higher frequency than at least one other. That's it. In order to figure out whether it's just two categories that differ or they're all different from each other, you've got to do post-hoc tests after rejecting the omnibus null hypothesis to find those specific differences. And it's pretty easy for this one. So your decision rule is if your asymp sig, that's just what it calls it, asymptotic sig, is less than 0.05, reject the null. the frequencies are not all equal across categories if you do that. So there's at least one difference across the categories' frequencies. If, however, a simp sig is greater than 0.05, the frequencies are basically equal across categories. Okay. So if you do, if your a simp sig is less than 0.05, you reject the null. You've got to figure out, all right, which categories are different, the weird ones. You're going to look at the residuals. The residuals are the difference between the observed and expected frequency for a given cell, and that expected is what you'd expect if the null hypothesis were true. And this helps you determine where the differences lie, like what are the weird cells is the easiest way to say that. So bigger positive or negative differences mean that that cell is more important for the chi-square being significant. The measure effect size, there isn't one. APA format, chi-square, you can use x squared if you can't find it in your when you're writing it up, but basically there it is, degrees of freedom, total sample size is n, chi-squared to 2 decimal points, p less than or greater than 0.05. All right, pretty straightforward. Let's go ahead and do one of these. So we're going to do the DMV written driver license test, and the question here is, there's 3 possible answer choices, A, B, and C, and there's 36 questions in 10 different forms. That's 360 total questions. Now, is A, B, and C equally likely to be the correct answer across all 10 forms? So that would be a good test practice to randomly assign the correct answer choice, but having done this, I can tell you the problem is, like, speed limits are in there, and it's kind of hard to come up with goofy low speed limits so that you can equally randomly assign A, B, and C to be correct answers. So let's see how we did. So if indeed this was true, that the correct answer, A, B, or C, was equally likely to be the correct answer, what would you expect the distribution of items to be across A, B, and C as the correct answer? Well, here's what it actually is. So for A, there was 105 of the 360, for B 142, and C 113, and you can see the percentages there, 29, 39, and 31. So the expectation would be that about a third of each of the items would be in each category of correct, right? So about 120A, 120B, and 120C would be the correct answer if you truly randomly assigned them, and each category was equally likely to be the correct answer. So they do differ from that. Some are lower, some are higher. The question is this just a chance difference, or is this a real difference? Like, is this a couple extra red Skittles, or is there no way that the correct answer was equally likely to be A, B, and C? So the expected values are, again, 120, 120, 120, and that's a third in each of those categories, and there is definitely a difference. Is it significant? So your hypotheses, there's 3 answer choices, so we got frequency 1, 2, and 3. Your null is that the frequencies in the 3 categories are all equal. Your alternative is that they're not all equal. Again, it's an omnibus test. It's either yes, no for this. So the frequency distribution of correct answers looks like this in SPSS. There was 105, 142, and 113 again. It's just a repeat of what was on the last slide. Excuse me, and the frequencies are not all 120 with 33%, as would be expected if the null hypothesis were true, that the frequencies were all equal. So even when you randomly do things, they differ by chance. You learned that earlier in the semester. So are these differences big enough from differences from 120 big enough that there's no way they're just a chance difference? We screwed up basically, because it looks like B is the correct answer 39% of the time, and that's more than A at 29 and C at 31. So here's the actual chi-square test that comes out of SPSS, and there's our observed ends again. So can we reject the null that answer choices A, B, and C were equally likely, within reason, to be the correct answer on the DMV written test? And the within reason means, there's always a little bit of chance up or down. So is this difference big enough that we can say it's real? That's why we do the test, because we're bad at judging probabilities. So there is the sig value in the test statistics for the chi-square, asimp sig as promised. Our decision rules again. If asimp sig is less than 0.05, we're going to reject the null. If it's greater than 0.05, we'll retain the null. So our decision here, well, 0.042 is less than 0.05, not by much, but it is, so we're going to reject the null. That is, the distribution of correct answers is not equal across A, B, and C answer choices. So post-hoc, we know that the frequencies aren't equal across categories, so what we have to do is look at these residuals over here to identify whether there are large positive or negative differences to determine where the weirdness is. And so you look at the numbers and the residual, and it's literally just observed minus expected here. And it's the difference, it's the residual. So there was 15 fewer A's, 22 more B's, and 7 fewer C's than expected if the null were true, that they were equally distributed across categories. And so the simple answer here is B was chosen more as the correct answer than A and C. And so if you don't know the answer on DMV's written test, apparently guess B. So that was one of the old rules back in the day anyway. And that's basically chi-square. So how do we just write it up real fast? So here's those same things, correct answer and your test statistics. There is no measure of effect size, so we just got to figure out our APA format. There it is, all filled out in pretty. 2, so degrees of freedom, 360 is our N. Our chi-square is 6.32, and because our sig value is less than 0.05, we put P less than 0.05. And that's it. That's chi-square goodness of fit test. So now let's talk about the chi-square test of independence. You use the chi-square test of independence when, again, you've got frequency counts, but you have 2 or more nominal or categorical variables. So goodness of fit was when you only had 1, right? Now you got 2 or more nominal or categorical variables, and you want to know if the variables are independent or if they're related. So some examples. In a survey of adolescent females and males, there's a nominal variable, right? Is there a difference in their self-perception of body weight, underweight, normal, or overweight? So that's 3 levels, technically ordinal. Does perception of body weight depend on the sex of the respondent or not? So you'd be looking at the distribution of persons across sex and across body weight. So it's a 2 by 3. And then here's the one we're going to do because it's totally fun. Were higher SES passengers more likely to survive the Titanic disaster? Let me think hard about that. Another way to say it is, were passengers of different SES levels equally likely to survive the Titanic disaster, or did survival differ across SES levels? So one variable here is your SES, that's 3 levels, right? And you're in a category. And the other one is survival, yes or no. You either died or lived. And so you got, again, 2 by 3. So the assumptions are exactly the same as the other chi-square, so they're weird. Independence, that is, you have a between subjects design, each thing or person's only counted once. The expected frequencies for each category are at least 1. And no more than 20% of categories have an expected frequency less than 5. So if you run into number 3 there, you just start combining categories, right? Is basically what you do, so you can still do the test. It's a weed whacker test. So your hypotheses for this are written using words, not mathematical symbols. So your null is something along the lines of the variables being studied are independent / not related. So you got to come up with a way to say that using the study variables specifically. So for example, SES of Titanic passengers was not related to their survival. There's my 2 variables. I'm saying they're not related, they're independent. Your alternative is the variables being studied are dependent / related. So for example, the SES of Titanic passengers was related to their survival. So there's a lot of different ways you can write these because it's words, but make sure to always name the variables being studied when you do it. So in the examples above, they both mention SES and survival, right? So this chi-square is also an omnibus test of a hypothesis. It tests many things at once. When you reject the null, all you know is that the variables are related. So there is some sort of relationship. Could just be, again, 2 categories differ. They could all differ. You don't know. You've got to do post-hoc tests after rejecting the null to find the specific differences. So our decision rule is the same, except it's called a Pearson chi-square asymp sig. If it's less than 0.05, you reject the null. Your initial conclusion is, yep, the variables are related. When you reject the null, you say, yes, they are not independent, they are related. Alternatively, if your Pearson chi-square asymp sig is greater than 0.05, you retain the null. The variables are not related. There's nothing going on here. The distributions do not differ across the other variable. Your post-hoc test is something called this adjusted standardized residuals, and each cell gets one of them. SPSS just calculates them, and you look at them, and they're kind of like z-scores, and they're z-scores of how much the observed frequency in that cell differs from what would have been expected if the null was true, the null being there's no relationship. So just like a z-score, if you get an absolute value of an adjusted residual that's greater than or equal to 2, then something's really weird in that cell, so you want to take a look at it. So positive adjusted residuals tell you that that cell was higher than expectation, and negatives adjusted residuals tell you that that cell was lower than expectation. And so they kind of say, look at the cell and see what's going on because something weird happened. Either it was too high or too low. So we use these adjusted standardized residuals to identify which cells had higher or lower percentages than would have been expected if the variables were not related. So they sort of cue you in on where to look to figure out why the chi-square was significant. There is a measure of effect size. It's called Cramér's V. In SPSS, it's called V, Cramér's V. So I don't know why. They just chose to do that. The good news is SPSS calculates it. It's right on the output. You don't have to do any math on your calculator. And it indicates the percentage of variability in the frequency counts accounted for by the relationship between the variables. So it's kind of like eta squared or omega squared. APA format for the chi-square is similar, except you got V on the end here. The chi-square of degrees of freedom, total sample size equals to the chi-square value to 2 decimals. P less than or greater than 0.05, and then you throw in V to 2 decimals. So let's go ahead and do one. Were upper, middle, and lower socioeconomic status passengers equally likely to survive when the Titanic hit the iceberg in 1912? We've all seen the movie, right? So the variables in here are your independent variable anyway is SES. That would be represented by passenger class. So it's kind of a proxy. First, second, and third class. Third's actually called stowage. So it is a proxy for high, medium, and low SES because prices went down as a function of left to right. Your DV is survival, and it's dichotomous and nominal. You either survived or you died. So you got a 3-level independent variable categories. Technically ordinal, but close enough. Your DV is nominal as well, survived or died, and each person falls into one combo of the crossing of these two things, right? You're either first class survived, first class died, second class survived, second class died, third class survives, third class died. And so it's counts of people. The hypotheses, again, are in words. Your null says there's no relationship between your SES and survival somehow, so I chose to say upper, middle, and lower SES passengers were equally likely to survive when the Titanic hit the iceberg. Think we're going to be rejecting that? The alternative is upper, middle, and lower SES passengers were not equally likely to survive when the Titanic hit the iceberg. So if we reject the null, we got to then do our post-hocs. So the chi-square test of independence doesn't have its own menu. You actually get it under a procedure called crosstabs, which is under descriptives. So this is what you get. This is a cross tabulation. This is called a 2x3 cross tabulation. You got whether they died or survived on the left side. So those are the rows. The columns are the cabin class of the traveler. So that's first, second, or third class. And you must request the appropriate row or column percentages to give you the percent within each IV level. So it varies. Sometimes you need the column percentage, sometimes you need the row percentage. You kind of got to look and figure it out. But when you don't have equal numbers, you get problems. So here I did column percentages, that is the percent within class of traveler, because there were different total numbers of passengers in these 3 SES levels. There was 325 first class, 285 second class, 706 third class. And the problem is, if you just compare raw counts, all things being equal, there's going to be more people surviving in the group that's bigger, right? Turns out this is a really good example because that's not the case, but normally that would be the case. So you do have to be careful. So 62.5% of the first class folks survives, 41.4% of the second class, and only 25.2% of the third class. So those sure seem different, right? Note we did percents, we didn't do raw counts of things. because they differed again. There was different numbers of passengers in each class. So could these differences just be due to chance, like having a couple extra red Skittles or fewer red Skittles in third class? Or, really was SES associated with your likelihood of surviving on the Titanic? So here's the actual chi-square test, and it gives you multiple rows here, 3 different rows. So our null hypothesis, again, is can we reject the null hypothesis that upper, middle, and lower SES passengers were equally likely to survive when the Titanic hit the iceberg? We're going to use this Pearson chi-square row of results right here. That's the one you want. So our decision rule again is if A simp sig is less than 0.05, reject the null. If it's greater than 0.05, retain the null. So, yep, 0.000 is definitely less than 0.05, so we're going to reject the null. So we know that passengers are not equally likely to survive across SES levels. That is, SES and survival are indeed related. So who was more likely to survive? Well, now we got to do post-hoc tests by inspecting the adjusted standardized residuals to determine which SES levels were more or less likely to survive. That's the next slide. So we're going to inspect the adjusted standardized residuals, and they're actually already in this table. I don't know if you noticed them. They're in the rows called adjusted standardized residuals. So we're going to find where the adjusted standardized residuals absolute value is 2 or bigger, and then we're going to look at the sign. If we see that it's a positive sign, we know there's more or a higher number in that cell than would have been expected if the null were true. And if we say negative sign, it's 2 or bigger, absolute value, we know that there were fewer in that cell than would be expected if the 2 variables had not been related. So they tell you where weirdness is. So if you get an adjusted residual where the absolute value is less than 2, it just means, that cell is consistent with the null hypothesis. That is that the 2 variables actually aren't related. So survival is dichotomous, and we run into this a lot. It's just 2 levels, right? And so you got to pick one side here. You want to talk about differences in people dying or differences in people surviving, but you don't want to do both because they're the flip side of each other. So among the first class passengers, we have an adjusted residual that's 10.5. So it's bigger than 2, right? So there was a higher number of people in that cell than would have been expected if survival and SES were not related. 62.5% of them survived. Among the second class folks, we have adjusted residual that's only 1.4. That's less than 2. So basically what that means is that 41.4% that survived among the second class is what you would have expected roughly if SES and survival on the Titanic were not actually related. So that one fits with the null, so it's not weird. It's not a weird cell. How about third class? Well, third class is negative 10.2. That means it's negative, so that means there was fewer in that cell than would have been expected if survival and SES were not related for the Titanic passengers. So we got more first class survived, fewer third class survived, and second class is about what would have been expected if SES and survival were not related. So our measure of effect size is Cramér's V, and it comes right on the output. There it is, 0.318. And that's, if you just multiply it by 100 and round it, it's roughly 32%. The variability in survival was accounted for by the passengers' SES on the Titanic. It's real data, by the way. Your APA format, there's the basic form. There's our results. Remember, we use that chi-square row. There it is all filled out. Where does it come from? We have 2 degrees of freedom, total sample size of 1,316. I didn't include people who worked on the boat, on the Titanic, just the passengers. There's our chi-square value rounded to 2 decimal points. Our P was significant, so we use less than 0.05. And finally, our Cramér's V is 0.32, so we throw that in there, round it to 2 decimals, and that's it. So the end result here, what you tell grandma, is that higher SES passengers, 62.5%, were more likely to survive than lower at 25.2%. So if you're Rose, you're more likely to survive basically than Jack. However, if you're in the middle class of the ship, you sort of survived at the rate you would have expected. Remember, their standardized adjusted residual was not bigger than 2. So there are some other non-parametric weed whackery sort of weird tests that I want you to know about, but this class is already crazy. So in the matrix of basic statistical tests, there was one called the Mann-Whitney U, and it was the non-parametric test used to compare two independent groups of samples, particularly when you've got an ordinal DV. And you also use it when you wanted to use independent samples t-test, but the data severely violated the homogeneity assumption, or you had really small and unequal sample sizes, whatever it is, you didn't fit the assumptions. So it is the non-parametric equivalent of the independent t-test. And it's Mann-Whitney U, and it's the one right above it in the matrix of statistical tests. So other non-parametric tests of note is the Wilcoxon Matched-Pairs Signed-Rank Test. That's the one that's above paired samples t-test. It's a non-parametric test used to compare two dependent, so you got a within design, groups of data, particularly if the DV is ordinal. And again, you can also use it if you wanted to use a pair T, but you couldn't because you violated homogeneity or normality and you had small crappy sample sizes or whatever. You can always, you always got this backup called Wilcoxon's Matched-Pairs Signed-Rank Test. So it is the non-parametric equivalent of pair T. And there's a couple others that I'm not even going to talk more about, but note there is Kruskal-Wallis H and Friedman Ranks, and those are the non-parametric equivalents of one-way between subjects ANOVA and one-way repeated measures ANOVA. Just know they're there in case you need it during your dissertation and they tell you you can't do the ANOVA you wanted to. Maybe you can use one of these and it might save you. So that's it on non-parametric tests. Pretty straightforward stuff. If you have any questions, put them in the discussion and I'm happy to answer them.